Welcome to the Formula Foundation. This video contains first, let's see the formal definition of inner product. An inner product on a real vector space V is a function that associates a real number, this real number, with each pair of vectors u and v in the vector space V in such a way that the following axioms are satisfied for all vectors u, v and z in V and all scalars k. And axioms are, first axiom is Symmetry Axiom, and second axiom is Additivity Axiom, third Homogeneity Axiom, and fourth axiom is Positivity Axiom. And a real vector space with an inner product is called inner product space. Means inner product एक function है. And what is function? Function is nothing but input, process and output. It is called a function. So inner product एक ऐसा function है जिसमें अगर हम vector space V से कोई से दो vectors as an input लेते हैं तो as an output हमें एक real number, इस तरह से एक real number मिले कि ये axiom satisfy हो, then function is called the inner product. Now let me take two vectors. Let's suppose we have two vectors. In RQ, and that two vectors are u, and coordinates of u are u1, u2, u3, and second vector is v, and coordinates of v are v2, v3. Now let me take the dot product of these two vectors. I hope you are well aware with the term dot product. So let me take the dot product of these two vectors. So u dot v will be u1 v1 plus u2 v2 plus u3 v3. It is the dot product of these two vectors u and v. अब हम इस dot product पर inner product के 4 axioms चेक करते हैं. तो first axiom है Symmetry Axiom. So in terms of dot product, Symmetry Axiom will be u dot v is equal to v dot u. Means we are required to prove that u dot v is equal to v dot u. So let me prove. Taking left hand side u dot v, and u dot v is equals to u1 v1 plus u2 v2 plus u3 v3, and we can write u1 v1 as v1 u1 because multiplication is commutative, so we can write v1 u1 instead of u1 v1. Similarly, we can write v2 u2 plus v3 u3, and it is equal to dot product of v and u. So u dot v is equal to v dot u, or it is equal to right hand side. It means that dot product is symmetric, right? Means axiom 1 holds. Now let me check the second axiom. Now second axiom is Additivity Axiom, and according to Additivity Axiom कि अगर हमारे पास 3 वेक्टर्स हैं तो अगर हम पहले फर्स्ट 2 वेक्टर्स का सम करें और फिर उसके साथ थर्ड वेक्टर की प्रोडक्ट लें तो वो इक्वल होगा कि हम फर्स्ट वेक्टर की थर्ड वेक्टर के साथ प्रोडक्ट लें और फिर सेकंड वेक्टर की थर्ड वेक्टर के साथ प्रोडक्ट लें और फिर उनका सम करें तो वो दोनों इक्वल होंगे. सो सेकंड एग्जाम इज एडिटिविटी एग्जाम. And in terms of dot product, additivity axiom will be u plus v dot z is equal to u dot z plus v dot z. And for dot product, we are required to prove this additivity axiom. So taking left hand side, so first sum two vectors u plus v. U plus v will be u1 plus v1, u2 plus v2 and u3 plus v3. It is the sum of these two vectors u and v. Now take the dot product of this resultant with the vector z. So u plus v dot z is equal to u1 plus v1 times z1 plus u2 plus v2 times z2 plus u3 plus v3 times z3. It is the dot product of u plus v with z, right? So when we simplify it, we will have u1 z1 plus v1 z1 plus u2 z2 plus v2 z2 plus u3 z3 plus v3 z3. Now we can rewrite this expression as u1 z1 plus v1 u2 z2 plus u3 z3 and plus v1 z1 plus u2 z2 plus v2 z2 plus v3 z3. Now notice that these three terms is equal to u dot z, means when we take the dot product of u with z, we will get this expression, plus, and when we take the dot product of v with z, then we get this expression, means we can write this expression as v dot z. So additivity axiom has been proved because it is equal to right hand side, means axiom 2 holds for dot product, right? Now third axiom is homogeneity axiom, and according to homogeneity axiom, अगर हम फर्स्ट वेक्टर को किसी स्केलर k से मल्टीप्लाई करें और फिर उसके बाद सेकंड वेक्टर के साथ प्रोडक्ट लें, तो वो इक्वल होगा कि आप पहले दो वेक्टर्स की प्रोडक्ट लें और फिर उसको उस स्केलर से मल्टीप्लाई करें. सो थर्ड axiom is homogeneity axiom. Homogeneity axiom. And in terms of dot product, homogeneity axiom will be k times u dot v is equal to u dot v times k. So let me prove it. Taking left hand side, so first we multiply the vector u with scalar k. K times u will be k u1, k u2, k u3. Now take the dot product of ku with v. Ku dot v is equal to ku1 v1 plus ku2 v2 plus ku3 v3, right? Now taking k as common, so k times u1 v1 plus u2 v2 2 plus u3 v3. So you know u1 v1 plus u2 v2 plus u3 v3 is equal to u dot v, means k times u dot v, and it is equal to right hand side. So it means homogeneity axiom for dot product also holds. Axiom 3 also hold. Now what is fourth axiom? Positivity axiom. And according to this axiom कि जब आप किसी वेक्टर की उसी के साथ प्रोडक्ट लेंगे तो वो नॉन नेगेटिव होगी, मीन्स या तो ज़ीरो होगी या फिर पॉजिटिव होगी. सो फोर्थ axiom is positivity axiom. And in terms of dot product, positivity axiom will be u dot u is greater than or equal to 0 and u dot u is equal to 0 if and only if u is equal to 0. So yes, in dot product, u dot u is equal to u1 square plus u2 square plus u3 square and it will be greater than or equal to 0. Why? Because जब हम किसी नंबर का स्क्वायर करेंगे तो वो हमेशा पॉजिटिव होगा और जब आप 0 का स्क्वायर करेंगे तभी हमें 0 मिलेगा. So axiom 4 also hold for dot product. अब क्योंकि डॉट प्रोडक्ट एक फंक्शन है जो कि इनर प्रोडक्ट के तमाम एक्सियम्स को सेटिस्फाई कर रहा है, इट मीन्स डॉट प्रोडक्ट इज एन इनर प्रोडक्ट एंड इट हैज़ अ स्पेसिफिक नेम, दैट इज डॉट प्रोडक्ट इज ऑल्सो कॉल्ड यूक्लिडियन इनर प्रोडक्ट. यू कैन राइट द केस वेयर प्रोडक्ट ऑफ u and v is equal to u dot v is called Euclidean inner product. Euclidean inner product, which is a special case of a general class of inner product in Rn, right? You can write inner product. So dot product is an inner product. because all the axioms of inner product hold. Right. Now length and distance in inner product space. So let me have two vectors u and v. Coordinates of u are u1, u2, u3, and vector v, coordinates of v are v1, v2, and v3 in R3. Now how we define the length or magnitude of a vector? You know, length of vector is the square root of the u1 square plus u2 square plus u3 square, and length of v will be v1 square plus v2 square plus v3 square. But observe that you can write it as magnitude of u is equal to the square root of the inner product of u to itself. Means when you simplify it, you will get the same result. Means u dot u whole power 1 upon 2. It means length of a vector in terms of Euclidean inner product is defined as the square root of the Euclidean inner product of u with itself. And what about the distance between u and v? You know, distance between 2 points in R cube is defined as distance in R cube. Distance between u and v is equal to u1 minus v1 whole square plus u2 minus v2 whole square plus u3 minus v3 whole square. It is the distance between u and v. But you know, you can write this as, that is distance between u and v is equal to u minus v is equal to u minus v dot u minus v whole power 1 upon 2. You can verify this. So we have defined both length of a vector and distance between two vectors in terms of Euclidean inner product. But have you ever listened the term norm of a vector? What is meant by the norm of a vector? Let's see. So norm and distance. If V is an inner product space, then the norm or length of a vector u in V is denoted by this notation and is defined by norm of u is equal to the square root of the inner product of a vector u to itself. And the distance between 2 points means vectors u and v is denoted by this notation and is defined as distance between u and v is the norm of the difference of these two vectors. Means inner product तो डॉट प्रोडक्ट भी हो सकती है या फिर कोई और प्रोडक्ट जो इनर प्रोडक्ट के एक्सियम्स को सेटिस्फाई करे. मीन्स तमाम इनर प्रोडक्ट के लिए किसी वेक्टर का नॉर्म किस तरह डिफाइन है कि स्क्वायर रूट ऑफ द इनर प्रोडक्ट ऑफ द वेक्टर टू इटसेल्फ. एंड हाउ वी डिफाइन द डिस्टेंस बिटवीन टू वेक्टर्स? नॉर्म ऑफ द डिफरेंस ऑफ टू वेक्टर्स. अब अगर इनर प्रोडक्ट डॉट प्रोडक्ट हो मीन्स यूक्लिडियन इनर प्रोडक्ट हो, देन दिस नॉर्म इज कॉल्ड द यूक्लिडियन नॉर्म एंड द डिस्टेंस इज कॉल्ड द यूक्लिडियन डिस्टेंस. And we use them to find the length of a vector and distance between two vectors in the Euclidean n space. We will see later how we define the norm and distance in this space other than the Euclidean space. Now let's see the inner product on the set of continuous functions over the interval from a to b. So here is an example. Let f and g be two functions in the set of continuous functions from a to b, and the product is defined as the integral from a to b of the product of f and g. Check whether the formula defines the inner product on the set of continuous functions from a to b. You know what is meant by the continuity of the function at a point. So what is continuity at a point? A function f of x is said to be continuous at a point x naught if the following conditions are satisfied. That is, f at x naught is defined and limit at x naught exists, and the limit of the function at x naught is equal to the value of the function at x naught. मीन्स अगर किसी फंक्शन की इस पॉइंट पर x नॉट पर ये तीन कंडीशन सेटिस्फाई होंगी तो फंक्शन एक पॉइंट पर कंटिन्यूस होगा. और इंटरवल में कंटिन्यूटी का क्या मतलब है कि फंक्शन इंटरवल के हर पॉइंट पर कंटिन्यूस हो. नाउ यू कैन राइट दिस इंटीग्रल इज वेल डिफाइंड since the function in the set of continuous functions from a to b are continuous, and we shall show that this formula defines an inner product on this set by verifying the four axioms of inner product for functions f is equal to f of x, g is equal to g of x, and we have taken the third function s is equal to s of x in this set of continuous functions from a to b, right? So let me check. First axiom is symmetry axiom. So for this integral from a to b f of x g of x, you know कि प्रोडक्ट किस तरह से डिफाइन है इस इंटीग्रल के फॉर्म में. सो इंटीग्रल फ्रॉम a to b f of x g of x dx, or you can, because functions are continuous, so you can write integral from a to b g of x times f of x, means commutative property hold. So you can write this integral as g of x times f of x, and it is equal to the product of g and f, right? And it is equal to right hand side. It means symmetric axiom hold. Now second axiom is additivity axiom, and for this we will take the integral of the product of f plus g and s. So it will be integral from a to b f plus g of x times s of x dx. Now you can use the property of the integral, so you can write this integral as integral from a to b f of x times s of x dx plus integral from a to b g of x times s of x dx, and you know it is the product of f and s plus, and it is the product of g and s, and it is equal to right hand side, means according to additivity axiom it must be equal to f plus g and s is equal to the product of f with s plus product of g and s, right? So it is equal to this right hand side, this. So second axiom 2 holds. Now third axiom is homogeneity axiom. So for this we will take the product of k times f and g. So it will be integral from a to b integral of kf integral of the product of kf and g, means k times f of x times g of x dx. So you can write it as k times integral from a to b f of x times g of x times dx, and it is equal to k times the product of f and g. So it is equal to right hand side, means for homogeneity we had required to prove product of kf times g is equal to k times the product of f and g. So it has been proved, that is axiom 3 holds. Now fourth axiom is positivity axiom, and according to positivity axiom product of v with itself must be greater than or equal to 0. So for this integral product of f with itself is equal to integral from a to b f of x times f of x dx, or it is equal to integral from a to b f square x dx. And to prove the positivity axiom we have to prove that this integral must be greater than or equal to 0. So it is given that every function in the set is continuous in the interval, and f of x is one of the function from the set. So because f is continuous, so it is defined everywhere in the interval. So अगर हम इंटरवल में से x की कोई भी एक वैल्यू लेते हैं तो उस x की वैल्यू पर f of x की कोई ना कोई वैल्यू होगी, मीन्स f of x is any real number at every value of x. अब वो रियल नंबर मीन्स एफ ऑफ एक्स पॉजिटिव भी हो सकता है और नेगेटिव भी हो सकता है या फिर जीरो भी हो सकता है. बट इफ वी टेक द स्क्वायर ऑफ दैट वैल्यू ऑफ एफ ऑफ एक्स then we must get a non-negative number. So you can write if f is equal to f of x is any function in the set of continuous functions from a to b, then f square of x must be greater than or equal to 0 for all x in the interval from a to b. Therefore product of f with itself is equal to integral from a to b f square of x dx is greater than or equal to 0. And according to the second part of the positivity axiom, किसी वेक्टर की उसी के साथ प्रोडक्ट तभी 0 होगी जब वो वेक्टर 0 होगा, and vice versa. And for this formula you can write further, because f square of x is greater than or equal to 0 and f is equal to f of x is continuous on the interval from a to b, it follows that integral from a to b f square of x dx is equal to 0 if and only if f of x is equal to 0 for all x in the interval from a to b. Therefore axiom 4 also holds. Means you have proved that integral from a to b of the square of the function must be greater than or equal to 0. And you know कि कोई ऐसा नंबर नहीं है जिसका स्क्वायर करें तो वो 0 हो except 0 itself. So positivity axiom also hold for this formula. So since the above formula satisfy all the inner product axioms, since the given formula satisfies all the axioms, so it is. Now if we are asked to find the norm of a vector in the set of continuous functions, then how we define norm of a vector in the set of continuous functions from a to b? Then how we define norm will be, you know, norm will be the product of u with itself whole power 1 upon 2. So norm will be product of f with itself whole power 1 upon 2 or square root, or it can be written as integral from a to b f square of x dx. Remember that it is not the Euclidean inner product. So I hope you got it. That's it.